Well, good afternoon. Welcome to the Kickoff event of the CyberGIS Center for Advanced Digital and Spatial Studies. And I'm very thankful for your being here, and we are all thrilled to be part of this. I'm Xiaowen Wang. I'm a professor of geography and geographical information science, and also a staff member of NCSA. I'm the director of this center. It's my great honor and pleasure to introduce our Vice Chancellor for Research, Dr. Peter Schiffer. Peter is a physics professor here, renowned physicist, particularly in the domain of condensed matter. Don't ask me what that is. Peter is one of my bosses, starting from last summer when we began operating this center, and I say the least that Peter's support is so instrumental to the establishment of this center. Without further ado, Peter, give us a few remarks. Thanks so much.
Yeah. Thank you. All right, thanks, Xiaowen, and I have to say that this is very much like giving a freshman physics lecture where, you know, the seats in the back are filled, and there's sort of a density distribution where, you know, the maximum density in the back, and then it kind of stays level, and then up at the front the density is very sparse, so it feels very comfortable here. So first of all, let me say welcome to University of Illinois at Urbana-Champaign. Those of you who are from out of town, and those of you who are part of the university, welcome to this kickoff meeting. As Xiaowen said, this is very exciting. When the vision for the CyberGIS Center was starting to percolate around, I guess about a year ago, and maybe a little bit more, you know, what was interesting to me was the breadth of interest and excitement that everybody had in seeing this take off. So, you know, there were, of course, folks from geography, and I expected them to be excited about it. But then NCSA spoke up and said, this is where we have to be. This is one of the most important topics where high-performance computing and big data are going to be key going forward in terms of scientific and technical applications. And then the Prairie Research Institute, which is our largest interdisciplinary research institute on campus, spoke up and said, you know, CyberGIS, we absolutely need that to get going on so many different fronts. They do all sorts of work in energy and environmental research, cutting across pretty much every discipline. And then there were all these other people, the Graduate School of Library and Information Science, people in engineering, people across the College of Liberal Arts and Sciences were excited about it. And this doesn't happen so often at a big university. A lot of times people are interested in their own individual area and not so interested in reaching out and connecting, but this topic brought it together. And after doing a little bit of reading and understanding a little bit more what CyberGIS is about, I understood why. Because using high-performance computing and our big data capabilities to figure out how geospatial information connects the dots really is going to be critical going forward. It's going to be critical for traditional environmental issues, land use issues, population issues, and sort of, you know, figuring out transportation networks, that sort of things, and of course the military applications, but also for all sorts of other things. So I was out there looking at the posters ahead of time, and, you know, there's a poster about snowplows going through the streets and figuring out where they are and why. And, you know, you can apply it to snowplows. You can apply it to pretty much any service that requires motion around a geographical area. To social media, which is the way that human beings communicate with each other. So it touches on the humanities and the social sciences. There was a poster about mobility, and that touches on not just the communication aspect, but also public health. So if we think about communicable diseases, and you remember the SARS scare that was several years ago, and you think about bird flu and various other communicable diseases. Understanding spatial patterns and place and motion makes all the difference, and the only sensible way to do that in the modern world is with high performance computing and big data, which is why this center makes so much sense at this time. Now, the University of Illinois at Urbana-Champaign is very well placed to make a big impact in this area. We have NCSA, which is the home of tremendous breadth of skills and talent in the computational areas, the big data areas. We have tremendous researchers across all the disciplines, geography of course, but all these disciplines that CyberGIS will be transformational for. And we have the leadership in Xiao Wen and the other folks who brought this center together to really make something exciting happen. So I'm thrilled to see it all come together. I mean, it's really great. And I just want to thank you all for showing up, for coming here for the kickoff. And so, some of you are just as excited as I am, so it was an easy thing. Others are curious and figuring it out, so it's a little bit of a stretch. But I'm glad you're here. And those of you who came from other parts of the country to be here, I'm especially grateful to you. We've got something very special going on here, and I'm really thankful that you're able to come and share the day and lend us your wisdom and insights, and hopefully you'll take back some, just a little bit of wisdom from our campus also as part of the bargain. So have a great day, enjoy it, and good luck with the center, shall I?
Thanks so much, Peter. Much appreciated. Know your schedule's very packed up, and your support is very important as we go forward, and very much resonate with what Peter has said, and very grateful for your participation as we launch this center to the next level. Any questions, comments so far? I'll give you a very quick introduction to the program we have here today. We will begin our keynote address after this, and we will have two panels convened this afternoon. One is from our external invited guests, the other one is campus researchers. And we'll have a poster session this evening, light refreshments reception that would run from 5 to 6:30. That would wrap up the whole program today. And questions, comments? If not, we'll move on to the next one. We are very fortunate to have Dr. Lynn Usery come over to deliver the keynote. It's my tremendous honor and pleasure to introduce Lynn, although that is a tremendous challenge to do this in a short time, and he has a long, distinguished career. He did his PhD in geography from, if I recall correctly, University of Georgia, and he was on faculty of Wisconsin-Madison and Georgia. What I admired Lynn most is he's moving freely between federal agency role he has had for many years and his university scholarship role, which he also had many years. And one of the challenges when I oftentimes parsed Lynn's many accomplishments is to figure out how many fellows he has been named for how many societies out there. I'll just name a few. He was one of the first class of fellows out of University Consortium of Geographical Information Science, and he was president of Cartography and the Geographic Information Society, and was also fellow there. But his energies out there, and he's been tireless serving the communities of geographic information science and technologies, and I think a lot of us in that community have been feeling the impact of Lynn's work and very much appreciate his service. So that's my rough stab of introducing Lynn, and I think in the interest of time, we'll just pass the floor to Lynn. Thank you very much, Lynn.
Well, it's an honor for me to be here, and I thank Shawan very much for inviting me to deliver this keynote. I thought an appropriate topic might be to talk about the need for CyberGIS, and we, the U.S. Geological Survey, is certainly one of the organizations that needs CyberGIS, and hopefully I can give you examples of why. So, what's the motivation for this? Well, there's more data. Much of the data is geospatial, location-enabled, higher resolution, three-dimensional, four-dimensional, volunteer geographic information, social media, more sensors of everything, all connected to become the Internet of Things, which requires CyberGIS and semantics to make sense of the 50 billion connected things that are coming about. So this is the motivation. What I'll try to do is to give you a little bit of a background as to why I think CyberGIS is very much needed at this point in time. Geography has been discovered. The bigger picture is big data, big spatial data, big data processing. I'll take one example that we're working with, the national map, and how we need CyberGIS to bring you the national map of the future. I'll also talk just a little bit about a study that was done by the United Nations on future trends in geospatial information management. And I'll end with the slide of CyberGIS as a solution. The world has discovered geography. There's been a growing recognition for a number of years among governments and private sector that an understanding of location and of place actually makes a difference. For those of us that have been associated with geography for a long time, we've seen this massive transition take place where the world at large has become aware of location and what geography means and what it can do. We now have citizens that have no expertise in geographic science that actually partake and use the technology in many different parts of their lives. They are contributing information that becomes part of our spatial data sets that we use. There's an often quoted statistic that 80% of all data has some locational component. Well, there was a recent study done by Hamann and Burkhardt that actually showed, for one broad example, articles published in Wikipedia, that it's closer to about 60% of those articles that have locational information are tied to location. However, 60% is probably more spatial data than we can actually handle, given the big data of today. So big data, 90% of it generated in the last 2 years, where data about individuals, groups, periods, all are combined into bigger groups and longer periods of time. I'm sure you're all familiar with the 4 V's of big data. This is a slide from IBM about volume, velocity, variety, and veracity. And it's interesting that these 4 items, I would have never thought this, but veracity may be the one thing that keeps national mapping agencies in business compared to the private sector. Something about authoritativeness of data. There's a lot of information on this slide, and I'm certainly not going to ask you to try to read all of it, and you can pick it all out. Just wanted to point to just a couple of examples from here that, if I can see this over. In 2008, Google was processing 20,000 terabytes, 20 petabytes of data on a daily basis. Facebook stores, accesses, and analyzes 30 plus petabytes of user-generated data. And it's on and on. And this is the big data environment. And I'll show you one other one that shows the rapid growth of this unstructured data. YouTube uploads 48 hours of new video every minute. 30 billion pieces of shared content on Facebook every month. If you go through these kinds of lists, you see the volumes of data that are there and how do we make sense of it, how do we use it. In other words, the amount of data in the world today is equal to every person in the US tweeting 3 tweets per minute for 26,000 years. Or every person in the world having more than 215 meter high resolution MRI scans a day. Or more than 200 high definition movies. would take about 47 million years to watch. So big data, it's out there. What's big spatial data? Geographic data of high resolution covering large areas creates big spatial data. I'll give you some examples. Remotely sensed images. This example from Denton County, Missouri, happens to be the county I live in. A fairly typical county for the Midwest, roughly a couple of thousand kilometers in, square kilometers in size. It takes 800 gigabytes of storage just to store 1 meter resolution color images for that one county. Those 1 meter color resolution images are the basis of the ortho image layer of the U.S. national map. They're repetitive coverage every 3 years of those images, and that coverage is 4 petabytes for the equivalent for the United States. Another type of our imagery at the Atlanta, we do urban area images. The city of Atlanta, the footprint of that city at a 0.33 meter resolution color images takes about 1 terabyte of data. And you can download all of these off of our websites. Be prepared for some long times to download. Satellite images with finer resolution than 1 meter, the stuff that Google puts out that you see, or Bing in their map products. LiDAR data of level 1, which is 8 points per square meter, or level 2, which is 2 points per square meter. And I'll talk about those in a little more detail later because they're a big part of our future. The USGS 3DEP program will use level 2 LiDAR for all of the United States except Alaska, in which we will use level 5 IFSAR data there. The data volume for the point cloud, the intensity images, and the Barrier elevation model is 7 to 9 petabytes of data. Processing and file creation usually doubles or triples the amount of storage that you need from the base data. Some other geospatial data, a little bit smaller in size, but nonetheless difficult to handle. Our standard USGS National Hydrography data set, based on the 1 to 24,000 scale topographic maps, is about 700 gigabytes of data. That's an equivalent resolution of about 12 meters if you put it in a raster resolution size, with an accuracy of roughly 25 meters root mean square error. So now we're projecting to use extract hydrography, the same kind of data, from level 2 LiDAR at better than 1 meter resolution. So going from 12 meter resolution to 1 meter resolution gives you 144 times the amount of data. In Dresden, Germany this summer, Franz Liebel at the University of Graz presented a view, his view of the future world called the virtual centimeter model, or excuse me, the virtual centimeter world model. It's a view of the world with centimeter resolution geospatial data, images, things like LiDAR, everything else at 1 centimeter resolution. According to Dr. LaBerrel and his backers, they say this world is coming, and it's coming soon. Can we store and process such data to a societal advantage? We'll talk about big data processing. Can the data be processed by divide and conquer? Right now, the USGS has many petabytes of geospatial data, but most of it is processed as 7.5-minute quadrangles, or as image tiles, or watersheds, or counties, or some other small geographical unit that brings the data down to a manageable level. The key question is, do you have enough data volume at a source to justify the use of big data processing, an average of, say, greater than 300 gigabytes? If you don't, then you can consider investing in a more traditional enterprise data warehouse. Moving big data. Most enterprise networks do not have the bandwidth to move big data among the different servers for processing. There are processing limitations. There are many people that are still working with the 2 gigabyte file limit. They can't handle a file larger than that because of 32-bit Windows limitations. This is a large set of data sampling from the U.S. Geological Survey. The ones on top in green are all layers of our national map, and I'll talk a little more detail about that. The others are all different kinds of data that we have for biology, water, geology, and those kinds of data sets. Most of these are nationwide data sets. They're all freely accessible. You can download them. Many of them qualify as big data just because of the size and the fact that they cover the entire United States. Talk a little bit about the national map. It's our primary focus within the National Geospatial Program of the U.S. Geological Survey. It includes 8 data layers, the 8 layers that you see here: land cover, structures, boundaries, hydrography, geographic names, transportation, elevation, and orthoimagery. It's public domain data, freely available. You can download all of it. It's used to create new 1 to 24,000 scale topographic maps and a number of other products and services at multiple scales and resolutions. The national map is built on partnerships and standards. It's not something that we develop ourselves. We get data from other people, put it together, and provide it to the public. Some of the products and services: the data products, the individual data layers, our national hydrography data set, our orthoimagery, our land cover data sets, and those types of things. And then there are the derived products, the U.S. Topo, which is our new generation topographic map, freely downloadable, a standard 1 to 24,000 scale. We do repeat coverage of the United States every 3 years. It took us over 50 years to get the first coverage once over. Now with digital technology, we do it every 3 years. We do complete coverage of the U.S. We produce over 100 maps a day, every day. And we have every historical topographic map that the USGS has ever produced is now available in digital form, and you can download it from our website. Our transportation data, boundaries and structures uses what's known as a best practices geodatabase model. Those are essentially support layers for most of what we do in USGS. Our primary data layers are hydrography and terrain, and the other layers are put there as reference for the main layers that we deliver. We do put structures on our maps. Now all of our structures are actually being generated by volunteers. We have a volunteer geographic information program where we accept data edits and updates to our existing maps through a volunteer program. All of our structure data are now collected that way, and we're planning to expand this to other areas as well. So to talk about elevation, I mentioned that's one of our primary data sets. It's also one of the ones that qualifies as big data. This slide essentially shows you where we are or where we have been for the last several years. Complete national coverage at 10-meter resolution. We have substantial data at 3-meter or 1/9 arc-second resolution. New data that was collected as part of this program was being resampled to the 1/9 arc-second. In Alaska, I mentioned before, it's 5-meter coming from IFSAR. We are delivering LiDAR point clouds as well as the elevation data according to a USGS specification. Well, we did a study a couple of years ago to find out really what the country needed in terms of elevation data. It was known as the National Enhanced Elevation Assessment. It involved a group of agencies in terms of their needs, and we looked at, excuse me, the study looked at 602 different mission critical activities that require enhanced elevation. 34 federal agencies, 50 states, a sampling of local governments, tribal governments, and private and non-for-profit organizations. The study came up with a conclusion essentially that a national program of this elevation data could generate $1.2 billion to $13 billion in new benefits each year if we made it fully operational. These are the kinds of business uses that would benefit from high-resolution elevation data for the entire country. Things like precision farming, geologic hazards mitigation, flood risk, those types of things. Well, I mentioned the quality levels before, and I'll focus here. The quality level that we're looking at is quality level 2, which is medium-high accuracy and resolution LiDAR data. It essentially has a point spacing, horizontal point spacing of 0.7 meters, and a vertical accuracy of about 9 centimeters. If we went to level 1 data, we'd have essentially 7 points per square meter, point spacing of about 0.35 meters, but we still have about the same vertical accuracy. Unfortunately, going to level 1 data costs a tremendous amount more than level 2. So the study arrived essentially at looking at different possibles of levels of data and the needs that we could meet about 58% of the requirements if we had quality level 2 data and we acquired it on an 8-year cycle. If we went all the way out to get quality level 1, yeah, the highest quality we could do that, but look at the actual cost in terms of the benefit, the ratio isn't there. So the cost-benefit ratio seems to pan out here. So that's when we settled for quality level 2. What does that mean? Well, it would cost us $146 million a year to generate those data, but the annual benefits from the data would be about $690 million a year. So it's about almost a 5-to-1 recovery ratio in terms of benefit. So based on that study, we have begun the 3D elevation program. The 3DEP, known as 3DEP, the 3DEP program essentially is one of 10 possible scenarios that came out of the study that was decided to be implemented. 3DEP will go online in January of 2015. All of our new contracts for LiDAR data are required to meet the specification of level 2. It'll be LiDAR level 2 over conterminous United States, Hawaii, and the territories on an 8-year cycle. IFSAR data over Alaska. We'll have the point cloud accessible, multiple derivative products, and then essentially, as I said, 3DEP is a program initiative that we're beginning January 15. So this is all essentially a basis of big data and big data processing and why CyberGIS is needed. Let me try to bring this down to a real example. Here's some real processing that we have done given standard desktop machines, and I want to try to translate that into what it will take to do the same kind of processing with the new data that we have. So I'm going to look at an individual subbasin of high resolution. Quote, high resolution now is 24K in our current databases, and then we go to even higher resolution, instead of 24,000, 2400. We call that local. So it's a little bit of a misnomer, but high resolution is 24K, 1 to 24,000 scale-based data from the National Hydrography data set. And it uses the 10-meter national elevation data set. So 10-meter resolution elevation data, 1 to 24,000 scale resolution hydrography data. We've developed generalization algorithms to actually take this to any scale that our users might want on both our map products and our web servers. So we take an area, an average size subbasin is about 3,200 square kilometers. I mentioned Dent County before, typical county in the Midwest, about 2,000 square kilometers. So a watershed's our subbasin's a little bit bigger, about 3,200 square kilometers. With our current data, the 24K and 10-meter NED, it requires about 3.6 gigabytes of disk space just for the integration, processing, and analysis. Includes about 4 to 5 hours of processing time to derive and validate 24K synthetic streams and about 1 to 2 hours of processing time for generalization enrichment and network pruning. These processing speeds are based on a 64-bit, 2.5 gigahertz machine with 16 gig of RAM. So it's taken us 7 to 8 hours just to do the processing for one subbasin to do run the generalization process on it. These are the kinds of tools that have come out of it, things that allow us to classify land types, develop catchments, do density partitions, upstream drainage areas, and correct gaps and center lines. Also to be able to automatically determine the stream center line delineation from the network of hydrography, and once you generalize it, you have to maintain that and be able to still generate those stream center lines. This is an example of a toolbox that's been generated as a part of this. And I'll point to these examples here because what we found is you can't have one algorithm and run it for the whole country. It is a site-specific problem. You have to know what the terrain is like and the weather conditions in the area in order to run an appropriate generalization algorithm to get the right kind of drainage for an appropriate scale. So if we go to higher resolution data, again, this was based on 1 to 24,000. If we go to higher resolution data coming from LiDAR, then we're probably going to have a lot more of these different areas that we have to consider because the data will be much more sensitive to climate and landform. But just an example, this is a toolbox that's been developed for generalization. So, big spatial data processing. Can we implement a similar set of tools for generating hydrography from level 2 LiDAR and then generalize that to desired scales and resolutions? It's a much different problem. The data for one watershed needs to be processed as a whole. It's not a divide and conquer problem anymore. We can divide and conquer so far down, but once we get to a subbasin area, we have to treat it as a whole. And if we have high enough resolution data for that area, then it becomes a big data problem. So divide and conquer only works so far. So this is a CyberGIS problem. Let me turn now to the United Nations study that was done on global geospatial information management, a 5 to 10 year vision. There's several things that come out of this, and many of you are probably familiar with some of this. Everything happens somewhere. There's an exponential growth both in the number of data capture methods and in the volume of data that's being generated. Most all of you probably have cell phones, and they all have global positioning capability built into them. That's not the only thing that has global positioning capability built into it. It's appearing everywhere. We're being bombarded with sensors from all sides. The average American car now, or the average car, new car has over 100 different sensors in it, and almost all of them have GPS built into them. The proliferation of low-cost network-enabled sensors, whether it's your mobile phones, computers, energy meters, or whatever, means that previously unimaginable data volumes are going to be created. Data creation is active, but it's also passive. If you use Twitter or if you use Facebook, then you're providing spatial information to those people that harvest those data. We're also seeing model geospatial actor data, information generated by individuals using websites and social media overlaid on top of spatially accurate geospatial information. These trends will continue from life-critical information to finding your favorite restaurant. All of this is being put out and made available in locationally enabled environments. The huge quantities of data that are now generated and increasing volumes of data that are likely to be created brings a requirement for enhanced data management systems. With approximately 2.5 quintillion bytes of data created every day, a significant amount of which has some kind of spatial location, the challenges of data management and data integration will be significant. So the need to address this problem is going to drive the trends in the next 5 to 10 years, an increasing use of reliance on big data technologies that enable analysis of vast quantities of information. And it has to be done within usable and practical time frames. So we can look forward over the next 5 to 10 years to massively scalable distributed systems for processing unstructured and semi-structured data, and these will be widely accepted and relied upon in management and interpretation of geographic information. This is not my telling you this. This is coming out of the United Nations study that pulled together about 50 to 60 people from all over the world involved with national mapping and geospatial data. So my statement here is CyberGIS comes of age. Linked data and the Internet of Things. Given the vast amount of data that's being generated, we need some way to make sense of it. One of the ways that's come about that offers an opportunity to make sense of the data is through linking different data sets together. Linked data is likely to increase significantly over the next 5 to 10 years. It offers the opportunity to connect data to other pieces of data on the web, contextualizing and adding value. Linked data works using essentially the resource description framework, the RDF, triple of subject, predicate, object, which is implemented on the semantic web. The link is a uniform resource identifier. It's like a URL, a standard web location that you go to, except the URI is a unique name rather than a unique web location. It's a unique name that allows you to locate that object on the web out of all of the different objects that are out there. Semantic technologies are going to play an important role in publishing and making sense of the data. And one of the things that ties it all back to geospatial is that location is the underpinning element in a lot of this. Linked data is built from ontology and semantics, allows automated machine processing and logic for query resolution and retrieval. One of the real values of linked data is that we can process it with machines and get answers out of it rather than having to have humans interpret it. The network of tomorrow is built on an increasing number of sensors and increasing data volumes, and this was kind of my opening motivation. The Internet of Things, with an estimate of over 50 billion things that are going to be connected by 2020. The omnipresence of geospatial information in our lives, whereby almost all pieces of data have some form of location reference, will continue, with location providing that vital link between the sensors that generate the Internet of Things and a uniform resource identifier that assigns a thing or an object that is connected to the world of things. Cloud computing. Managing and hosting and serving vast volumes of data today, this is likely to increase in the future. Over the next 5 to 10 years, all of these different cloud computing ideas, infrastructure as a service, platform as a service, software as a service, or data as a service, all of those come about. The problem for a lot of us is how do we get our data to the cloud and get it back down again when we want to use it? We're also seeing a proliferation of open source. Open source solutions are going to grow significantly. The open source geospatial community is already well established through the Open Source Geospatial Foundation. There are a number of national mapping and charting agencies in the world that are already using open source. We at USGS are starting to adopt open source in many of our software solutions. Open standards, the Open Geospatial Consortium, the International Standards Organization. Standards are going to be necessary for the revolution in data processing that has to happen. The compliance with Open Geodata interoperability specifications and with GeoSparkle. GeoSparkle is essentially the query language for the semantic web for geospatial location-enabled data. It is essentially the parallel to SQL for relational databases. We'll make it possible to develop interoperable technologies for maintenance of geospatial data as well as complex semantic analysis of both spatial and non-spatial data. In terms of data creation and maintenance, the trend from, I mentioned before, from 2D to 3D to 4-dimensional visualizations is both user and technology driven, and it's going to accelerate over the next 5 years or so. There will also be an integration of external 3-dimensional information with business information management systems that uses the internal and below-ground 3D to create integrated walkthrough models. And the use of the fourth dimension, time, is likely to increase in the coming years, with GIS companies increasingly providing time functionality as an additional dimension alongside the X, Y, and Z coordinates. Some other trends in professional data creation have to do with things like UAVs, unmanned aerial vehicles. In the civilian sector, these are likely to be increasingly used as additional methods of gathering data. The stumbling block right now is FAA regulations on releasing these things and allowing people to use them. Mobile mapping systems will be upgraded for capturing and processing both street-level visual data and points of interest and attribute information. So, where does this leave us? Technologies to handle big data. Well, I see CyberGIS as a solution. High performance computing, supercomputing, graphics processing units, massively parallel input-output, parallel TIFF writers, which we've already developed. We need parallel readers and writers for LAS files of LiDAR and for the compressed formats of LiDAR, the LAZ files. Semantics and ontology and data linking are needed for all of these things. And then quality assurance of things like volunteer geographic information and user-generated content so that they become authoritative data. And so we're already turning some of the volunteer geographic information into authoritative data through our USGS programs, and I think you'll see much more of that. So I think that the time has come for CyberGIS as a solution for our big data problems. Thank you.
Thank you for your nice presentation and letting us know that USGS is going to continue gathering at a was it QL2?
Right.
That pretty much provides data for how we used to do things and maybe some of the stuff that we do now. But it really doesn't kind of help us go much further for things that we might do, such as finding subtle depressions in fields that would relate to precision agriculture, some environmental issues. It doesn't help us a whole lot with places that are heavily forested. When can we expect to get a higher level of data and that will enable us to make progress on some of these problems and reduce pollution? Thank you.
What kind of data do you think you need?
I could use 8 points per square meter, and that would be very helpful to me. 4 points per square meter would be an improvement, but that's my own personal needs for work that I'm doing. Thank you.
But you're talking about LiDAR data.
Yes, sir.
Okay. Yeah, and I would agree with you. There are cases where you do need level 1 LiDAR data, 8 points per square meter. Unfortunately, in terms of a national program, there's no way to justify that with the benefits that would be accrued from that, at least according to the National Enhanced Elevation Study that was done. And it was a very comprehensive study, so we think we're on pretty solid ground there. And again, that's not to say that it's not needed in specific areas, and it will be acquired in specific areas. In fact, we have some level 1 LiDAR data available right now in some parts of the country, but it's very limited simply because of the expense of gathering the data, and there has to be a requirement to justify that expense. So we would not be able to do it on a nationwide program. Even with LiDAR level 2, the nationwide program is $146 million a year for 8 years. That $146 million is over twice what the budget for the entire National Geospatial Program is that does all of the other mapping for the USGS. So just getting that data is far more in terms of budget than we would ever have available. And so LiDAR level 1 is out of the question in terms of nationwide program. Does that make sense? It's simply a financial argument. We can do it in specific places where something justifies it, but you can't do it for the whole nation because the cost would be exorbitant. It would be multiple $1 billion to get LiDAR level 1 for the nation.
Are there specific areas you were looking to, or is this just a broadly national coverage you are arguing or you are pointing to?
Well, I'm thinking specifically of the area where we're at right here in in the glaciated Midwest, where precision agriculture and what's the term that I'm looking for, where you apply pesticides, herbicides, fertilizers on the basis of a GIS and so forth. All of that it would help to reduce some of the need for over-applying certain types of herbicides, pesticides, and so forth, but also would help make better use of that which is applied. I mean, our program here is 1 point per square meter, and grant you it's an improvement over a topographic map, the old topos, but the needs could be, and I know of other environmental needs and even mineral exploration needs that could use this higher level of information right now.
Yeah, and you saw precision agriculture was one of the applications I had listed, and you're correct. It is one of the places where high-resolution elevation data could do a great deal of good. I was involved in the mid-90s in helping develop precision agriculture in cotton and peanut farms in South Georgia. And it's phenomenal the savings that come about both environmentally and economically by applying just what you talked about, the pesticides and herbicides where they're needed and in the amounts that they are needed, because you know from the geospatial data what happens in different parts of your field. So it is one of the promising applications, but we do need the high resolution elevation data for that.
Thanks, Lynn. Question?
Thank you for your presentation. I've been a frequent user of the national map, and it's been very beneficial and very helpful. But sometimes as I've made the progress from kind of experimental stuff where I'm working with it interactively to a more production or automatic system, you know, there's not the APIs to get to that data directly. Can you maybe speak to maybe some of the ideas that are coming out, maybe some of the future things we can look forward so we can really take advantage of that data in a broader way?
Yeah, and we have, actually there's a study ongoing right now to redesign our web interfaces and the viewer interfaces to actually provide some of the kind of capability you're talking about and to provide some APIs. Part of our problem that we run into in the USGS is there's only so much of that we can do before all of a sudden we are competing with private industry at providing products to users. So we're limited in what we can do, but we certainly realize the limitations of the systems that we have out there now in terms of APIs and being able to program them for other uses. So there is work going on to improve that, but there's a limit to how far we can go because of competition with private industry.
I'm a very heavy user of LiDAR data, and you spoke very briefly about moving big data.
Yeah.
Could you talk some about the infrastructure that we need for moving big data? Right now, I'm not seeing it. Could you talk some about that, please?
Actually, I'm probably not the person qualified. The person to tell you about moving big data is standing right here next to me, is Shawan. But let me tell you some of our problems and what we're having trying to do. We have, our biggest problem is moving data around. And right now, in fact, I sat yesterday with a couple of people looking at processing some LiDAR data and found out that out of a 200-second processing time, 120 seconds of that was moving the data across the network to get it to the point where you wanted to process it. Only 80 seconds was actually used in the processing. So moving the data is a major problem. And most enterprise network infrastructures right now are not built with things like CyberGIS in mind or big data in mind in terms of moving those large volumes of data. Essentially what we need are, my understanding is fairly limited of this, but you need larger pipes to be able to get more data through at one time. And I'm sure that Shawan and some of the others here can tell you much more about how it can be done. We are in the process of trying to upgrade our infrastructure in USGS. I work out of a facility in Rolla, Missouri. Our other major facility of the National Map operations is in Denver, Colorado. And we have trouble moving data from Rolla to Denver, and we wind up shipping a lot of our large data sets. We'll put it on a hard drive and ship the hard drive FedEx to get it to them because we can't do it on the network infrastructure that we have.
Yeah, so we had a little bit of experience working with the Lynn's group on moving some of Lynn's group's data or USGS data. So one of the unique characteristics of moving geospatial data is to recognize the data eventually going to be accessed in a relatively interactive fashion by a large number of users. So the network engineers, researchers here, for instance, at NCSA, when I collaborate or interact with these folks, the conventional wisdom from other science communities is, oh, I have a big chunk of data, I just move them through. Mission accomplished. That's not the case for geospatial data, because once we move a piece of data, there could be related data movement associated with that piece because there's some potential interactive analytics behind it. So there's this user interactivity, but also associated data movement because of the triggering of some particular piece of data. So I think that's quite unique in terms of challenging the status quo of current network infrastructure going forward, dealing with big data analytics in the geospatial realm. I would say we're perhaps as a community scratching surface, which means whole lot of opportunities as well as challenges need to be tackled, but a completely fascinating new space we need to get into. Bob, you had some question?
Actually, I have two quick questions, Lynn. One deals with a comment that you made related to the ICA and work in the ICA around the centimeter map, which reminds me of the whole Digital Earth project from about a decade ago, and I'm wondering what happened with Digital Earth and how that relates to some of these conversations, because obviously you don't create a Digital Earth without a cyber infrastructure and CyberGIS. Second question deals with volunteer geographic information, VGI. So for 100 years now, we've looked to the USGS and all the smart people at the USGS to provide us with fantastic data, and we were convinced of the accuracy and the quality of that data, and we used it with great confidence. And now we're being told that citizen sensors and the public will be able to add data into the pipeline, which is a terrific idea in terms of democratization, but it raises some questions for those of us that came through that milieu about the quality of VGI, and if you might want to comment on that.
Okay, well, first on Digital Earth, I think a lot of what was proposed as Digital Earth 10 years or so ago, I think a lot of that is in place now. You know, in fact, there was something I was looking at just this week was when Google came out with Google Earth. Is that Digital Earth? Well, it's a piece of it. It's not everything. So, but I think a lot of what we aspired for Digital Earth 10 years ago is probably now in place. With respect to the volunteer geographic information, that's our biggest problem with taking volunteered information and putting it into the national map, is making sure that it is authoritative and meets our accuracy and standards requirements. We haven't folded on that principle. We still provide quality, authoritative data. Even though it does come from volunteers, it goes through a testing process, and we're actually using the volunteers in doing some of the testing to help us. And much like other organizations that use volunteer geographic information, you set up a hierarchy of trusted individuals and give them more rights in terms of editing and control of the data as they establish a record of trust that you can honor. So we have set up those kinds of procedures. It took us about almost 4 years to set up the VGI program. We had a VGI program long before VGI was called VGI, back in the 90s, and in USGS, where people would send us information to update our maps. We actually formalized that into what was known as the Earth Science Information Corps, that became the National Map Corps before our current VGI effort. And then we found out that we were getting all this information from the users, and we didn't have the internal staff to validate it all and to do the quality control and checking on it. So we shut down the program for a while until we could regroup, redesign the process so that people could enter data over the web, and we would have automatic checking of this by other editors and processors. And we came back and started only with structures. And we started out in a small area in 4 quads in Colorado, and then we expanded to a couple of counties in Colorado, and we went to the whole state, and then we went nationwide. But it was only after we assured that we had that control of the quality of the information. Now we're looking at expanding to other areas. We'll have to do the same thing for other kinds of things. Right now it's a fairly simple process where volunteers collect the location of structured information and the name associated with it and provide us that, and they can validate that against orthophotos and other sources. But as we expand, it becomes more complicated as to how you ensure the authoritativeness of the data.
Could you talk a little bit about your thoughts on data archival and storage? This is going to be, I mean, already I'm having terrible troubles with it, and this is almost certainly going to become a worse problem.
I didn't understand your question.
Data archival and retrieval, access, and so forth.
Data curation, preservation, as the data are being produced?
I guess I'm not sure what you're asking me to talk about. I mean, data archival and retrieval from, can you put it in perspective for me? Give me a context for what you mean.
Where are all of these data going to be stored? And I think at some particular point, there may be, repairs or updating or adjustments that are made incrementally. And all of these things may touch the stuff that people have copied or otherwise started using.
So maybe let me translate that question for you, Lynn.
Please.
So correct me if I'm wrong. So as USGS is putting together, say, for instance, a 3DAP program, producing this much data and perhaps related tools for the community. So what is the long-term strategy to keep this data alive, curated, improved, and evolving toward future needs that would have to be accommodated? So what is that long-term data asset being preserved and curated, and perhaps associated infrastructure that need to be planned along the way in place?
Well, maybe the way to look at that is take the example of our Aeros Data Center. That's exactly what the function of that center is. It's a data archival facility, been storing data since the Landsat program began, from the original Landsat, but all the other information that they have. And they have for a long time, Aeros has acted as a USGS repository for all of our different kinds of data, and things that, as technology has changed, they have migrated data from what was older photographic stuff was put in digital form, and then the digital form has been migrated to new types of digital form. We were storing on tapes, then we went to optical disc and things like that. Now it's all on disk media and those kind of things. So there is a process in place for all of the data that we have. We do not get rid of any data. We phase out a map or something like that. The older data is still there. I just mentioned our historical map scanning project. Every topographic map the USGS has ever created has been scanned and put in digital form and made available, and those are, you can get to them. So we are maintaining all of the data that we have, and none of it is lost, and it's done through a data warehousing process.
That perhaps answered your question? Okay. In the interest of time, I think we should wrap up. Let's thank Lynn again.